You type thread.start, compile your code, and assume the JVM neatly orchestrates parallel processing. But once it hits production, this high-level abstraction shatters. Code execution at this scale isn't a sequence of logical steps. It is a physical interaction with CPU architecture and memory controllers. To maintain performance, you have to account for 3 physical adversaries: CPU caching lines, aggressive instruction reordering, and the performance penalties of operating system synchronization. Java's high-level syntax often masks the underlying complexity of how these hardware components actually interact. Relying on these abstractions without mapping the hardware execution paths leads to system bottlenecks and race conditions that are difficult to replicate in testing. Before analyzing hardware mechanics, we have to look at how modern Java handles data deconstruction at compile time. We can see this in the implementation of Java 21's record patterns. Instead of just returning a Boolean, a Java 21 instanceof check embeds a record pattern to map the object structure. The compiler natively deconstructs the record, identifying nested objects and binding primitive coordinates, x1, y1, x2, and y2, directly to local variables. These variables are instantly accessible and strongly typed, which removes the need for manual defensive casting. Validating structural boundaries at the compiler level ensures the integrity of the data carrier before it is ever subjected to the complexities of concurrent execution. The JVM manages threads through a direct mapping. One Java thread corresponds to one native operating system thread. A thread begins in the new state upon instantiation. It only consumes CPU cycles when the OS task manager schedules it for a core slice, moving it into the runnable state. If the thread attempts to enter a synchronized block that is already held, it is forced into a blocked state, where it remains stalled until it can acquire the monitor lock. This is distinct from waiting or timed waiting. In those states, the thread has voluntarily yielded its execution, often through locksupport.park, and will not resume until it receives an explicit signal. Understanding these transitions is critical. Improper state management forces the OS kernel to frequently intervene, which limits the total throughput of the server. To coordinate these threads, we rely on the Java memory model. This is the formal contract that governs how thread private caches interact with global RAM. A common misconception is that standard operations like count++ are atomic. In a multi-threaded environment, this operation is a major source of data corruption. As this flowchart shows, the increment operation is actually 3 distinct bytecode instructions. The CPU must read the value, increment the register, and then write the updated value back to memory. When multiple threads execute these steps simultaneously, their timing can overlap. 2 threads might read the same initial value, increment it, and write back the same result, effectively deleting one of the updates. This overlap creates a data race, where the final state of the variable depends on the unpredictable sequence of thread execution. Because these mutations are fragmented at the CPU level, basic arithmetic cannot be considered thread-safe without external synchronization. Beyond atomicity, we have to address memory visibility, a problem caused by the physical design of the CPU. Modern multicore CPUs use isolated L1 and L2 caches to store local copies of variables. When a thread modifies a value, the change stays in its local cache to minimize the time spent writing to main RAM. If the flush to RAM is delayed, other threads running on different cores will continue to read stale data from their own local caches, completely missing the update. The hardware also introduces aggressive instruction reordering. The JVM and CPU operate under the as-if serial rule, which allows them to rearrange the order of your code to maximize throughput. This means the CPU might execute code in a different order than you wrote it, as long as the result appears the same in a single-threaded context. In a concurrent system, this reordering can cause an object to be visible to other threads before its constructor has finished initializing its fields, ultimately leading to completely unstable application states. The volatile keyword addresses these visibility and reordering issues, but it functions as a hardware instruction rather than a lock. When the compiler encounters a volatile variable, it injects hardware-level memory barriers, or fences, into the instruction stream. A store-load fence explicitly forces the CPU to immediately flush its local write cache down to the main RAM. Simultaneously, the fence invalidates the local caches of other cores, forcing them to pull the latest value directly from RAM during the next read. While volatile guarantees visibility and prevents reordering, it does not ensure atomicity. Operations like count++ on a volatile variable will still result in data races. For operations requiring full atomicity, Java uses the synchronized keyword, which manages locks through the 64-bit mark word of an object. To minimize overhead, the JVM uses biased locking, where it writes the ID of the executing thread directly into the object's memory bits, allowing that thread to reacquire the lock without extra instructions. However, biased locking is often deprecated in modern environments because the coordination required to revoke it when its second thread arrives is quite high. When a second thread contests the lock, the JVM escalates to lightweight locking. It uses a hardware compare and slock instruction to record a pointer to the locking thread stack. The contending thread does not suspend yet. Instead, it enters a spin loop, repeatedly executing CAS instructions, hoping the lock releases quickly. If the contention persists, the lock undergoes inflation into heavyweight locking. The JVM instantiates a native object monitor. Contending threads stop spinning and are moved into a blocked state queue managed by the operating system. This transition to the OS kernel introduces heavy context switching delays, which can significantly reduce the overall execution speed of the application. To avoid the costs of locking, developers often use ThreadLocal variables. However, in environments with persistent thread pools like Tomcat, this introduces a specific memory leak vector. Each thread maintains an internal ThreadLocal map to store its private data. The map uses weak references for keys, but actual data values are held by strong references. When a ThreadLocal variable goes out of scope, the garbage collector clears the weak key. However, the large data value remains pinned to the thread by its strong reference. In a thread pool, threads are reused rather than terminated. This means the orphaned data values are never collected, causing memory usage to climb steadily as the pool operates. Relying on automatic garbage collection in this scenario is insufficient, as the data is technically still reachable through the long-lived thread. Preventing these leaks requires explicit lifecycle management of the memory bound to each thread. This is achieved by wrapping ThreadLocal usage in a try-final block. By calling the remove method in the final block, you manually sever the strong reference, ensuring the data is eligible for garbage collection as soon as the specific task is finished. Robust concurrent architecture requires an understanding of how memory barriers and lock escalation impact the underlying hardware. Engineering for high performance means moving beyond high-level abstractions to manage the physical execution paths of the system.